Hey folks, today we're going to talk about nuclear bombardment reactions. This is the fourth podcast. Bombardment sounds like exactly what it is. There used to be a game called Bombardment, also known now as Dodgeball or something else. In a lot of schools it's banned, but anyway, the concept is hitting something with something else, like being bombarded with a ball or being hit with a ball. That's what it's all about. Right? So first let's remember what radioactive decay is. Radioactive decay happens spontaneously. In other words, it just happens. We don't make it happen, it just happens. That's the decay part. Right? Now, part of the problem with speed is we can't control the speed. Right? So if we say that carbon-14, for example, decays every 5,730 years, no matter what we do to carbon-14, we can't make that happen any faster. Right? So the speed is completely dependent upon the isotope. Right? So the isotope that we're dealing with is what's going to determine how fast this thing decays. It may be slow, it may be fast, but it is completely dependent upon the isotope, and there's nothing that we can do to change that. So could we change the isotope? Could we change what the thing is that is decaying? Well, that's exactly what the concept behind nuclear bombardment is. We want to change this to something else to make something that would give us a lot of energy. So that's the goal, is to go and put in a little bit of energy, change the isotope or change the element from one element to a different one, and then maybe it'll decay quickly. And that's what we want to figure out, or decay in such a way as to give us energy. Right? What do you notice about this guy? This is a picture. Okay, so it's not a painting or a drawing, it's an actual picture. So nuclear bombardment reactions are when an atom is bombarded or hit with a stream of particles, like alpha protons. That's supposed to be protons. That's protons. Alpha particles, neutrons, protons. Right? And in 1919, right, that's less than 100 years ago, Ernest Rutherford was the first to identify a nuclear bombardment reaction. And what he did was he took an alpha particle and he whacked it into nitrogen. Now when he did this, the two protons and the two neutrons that were there went into the nucleus, and it created fluorine, which was element number 9 with a mass of 18. If you look at the 4 plus the 14, they make 18, and the 2 plus the 7 make 9. The fluorine was then unstable, and it decomposed into oxygen, which is number 8, and it was oxygen 17, and a single proton, which was hydrogen. He created a very limited number of isotopes. Again, remember this is 1919, so he created some isotopes, and what he did was he created some isotopes that were not naturally occurring. So they didn't exist in nature, and if they had at one point in time, they decayed over time, so they were all gone, and we didn't see them anymore. But why would they not occur naturally in nature? Well, let's look at this nuclear bombardment reaction. Would it happen? Well, what are we doing? We're taking an alpha particle, which is somehow 2 protons and 2 neutrons, all right, without any electrons. So it's the nucleus of a helium atom, and somehow we're whacking it into nitrogen. And we have to whack it into the nucleus. So would this happen in nature? Frankly, probably not. All right? Why? Well, because you've got this thing which is positively charged over here. All right? It's got 2 protons. Well, let's draw it this way. It's got a proton and a neutron and a neutron and a proton. So you've got this thing which is a helium nucleus, and you're trying to whack it into nitrogen. Well, remember, nitrogen has 7 protons, and it's going to have 7 neutrons. So 7 positively charged things and 7 neutral things in here with a bunch of electrons running around it. All right? Well, of course, this is going to be attracted to the electrons, but what happens when it gets close to these protons? Well, of course, these are positive, those are positive, they're going to repel each other. So this is not going to happen very easily in nature, because these protons, when they come near these protons, are going to turn around and they're going to run away. All right? Because they're getting too close and they're being repelled. So chances are this would not happen very well in nature. So we can make it happen, but it's not going to happen easily in nature. So how could I get the alpha particles to move faster so they overcame that repulsive force? how could I take this alpha particle, which is all protons and neutrons, and somehow speed it up to hit this nitrogen? Well, I could do it a few ways. All right. One way to do it is temperature. And if I increase the temperature, if the temperature goes up, then the molecules move faster. So the hotter I make this, if I make this thousands of degrees Celsius, right, then I can make these molecules move faster. They'll whack into each other, and they might have enough energy to go and actually have the alpha particle go into the nucleus of the nitrogen. What else? Well, I could use magnets. And after all, this thing is positive. So if I put some positive magnets behind it, I'm going to push it a particular direction. So if I've got an alpha particle over here, and I put some positive things here, it's going to push it this way. And if I put some negative charges over here, it's going to pull it that way. So this thing can start to move, and I can move it faster by using positive and negative forces to push it and pull it along. Oh, that would work. But how many magnets would I need to make it move quickly? Well, there are in this world things called particle accelerators. Now this one happens to be, I think it's Switzerland, but it's somewhere over in Europe, and it's called the Hadron Accelerator. And you may have heard about it, especially if you watch Big Bang. They talk about the Hadron Accelerator pretty often. Sheldon mentions it. Right? This thing that you see right here, this whole line going all the way around, right, that's the accelerator. It's 17 miles long. So from this point over here until the electron or whatever it is gets back to that point, it's 17 miles. So if we put something in this thing, in this loop, if you will, and we start to push it along with magnets and pull it along with magnets of the opposite charge, right, then we can go and make it move quickly around the circle. Right? Now, to give you a sense of scale, this thing down here, you should be able to figure out that is an airport. All right, so that's a pretty big circle of an accelerator. Now, what's actually inside there? Well, inside there is this little tube, right? And this is the Hadron Accelerator, and this is really how big it is, and it is miles long, so they use bicycles to get around. But the entire accelerator is here, and they have electromagnets surrounding it to push the particles, whatever particle they happen to be working with, to go through this tube, which is all underground, to make it move faster. That's exactly what they're trying to do, and it's 17 miles long. So what happens as you accelerate those particles? Well, this is something that Einstein discovered, and again, his concept of energy equals mc squared. The more energy you put into this to move them faster and faster and faster, the more the mass of the particle increases. So the mass actually changes. So if I'm taking an electron, which has mass, and I go and move it faster and faster and faster, it never gets to the speed of light. Well, why is that? It's because its mass increases. So when you move it faster, its mass increases. You move it faster still, its mass increases still. So it takes more and more and more energy to move it just that little bit more faster. And so you reach a point where it's not moving any faster. But what happens when two particles collide when they're moving this quickly? Well, you get things called quarks, which are way outside the realm of our chemistry class, but that's something you might learn about in college because they are another type of particle that we have not talked about. And we can come up with antiparticles. In other words, if you can think of a proton and you think of a proton that is an opposite, a negative proton that would annihilate it, we've already talked about electrons that are negative, and we've talked about positrons, right, that annihilate each other and generate a whole lot of energy. Right? There are also other energy. They talk about the Higgs boson. They talk about this thing called a God particle, which they refer to sometimes in the literature. So there are lots of things that they can find when they whack these things together at tremendously high energy. So what nuclear bombardment works well? Well, think about it. If we've got an alpha particle is big and fat, it weighs a lot, it weighs 4 atomic mass units, and it has 2 protons. So the nice thing about this is it's positively charged, it has a 2+ charge, so we can use magnets to move it really, really well. The problem is it's big and fat, and it takes a lot of energy to whack it into something. And we have to overcome the repulsive force of this other nucleus here. all right? Because it doesn't want to go into that nucleus because they're both positively charged. How about a beta particle? Well, again, a beta particle is kind of cool. It has very little mass. It does have mass. It doesn't weigh much at all. It has a negative charge, so we again can push it with a hadron collider or some other mechanism to push it and make it move faster. But now all of a sudden you've got a nucleus that's positive, but around here you've got electrons which are negative. And these electrons, these high-speed beta particles, and these electrons repel each other. So as a result, the beta particle doesn't want to get in there either. Now, if it could get past all the electrons, it would be fine heading towards the nucleus, but it's still repelled. So what would work? Well, the one thing we haven't mentioned are neutrons. Neutrons have a mass of 1, but they have no charge. So if I go and I fire a neutron at this thing, well, it doesn't care about the electrons, so it just keeps running going. It doesn't care about the protons because it's not repelled. So with just a little bit of energy, I can take a neutron and I can hit it in to the nucleus of an atom. And that should change what the atom is if the neutron stays in the nucleus. So neutrons are excellent for neutron bombardment reactions. Now, why do we care about creating radioactive isotopes? Well, there are a few reasons. One is we can use them for research, okay, cancer research. And cancer research, cancer detection. So this is something that we can use isotopes for, all right? We can use them to generate energy, okay? And that's kind of where I want to go right now. Before we go any further, I want to talk about how different types of isotopes can release energy. Now, if we look at a normal chemical reaction like burning a piece of wood or burning a piece of coal or using natural gas to heat your home, right? An ordinary chemical reaction like that is going to produce on the order of 50 kilojoules per gram of coal or natural gas or whatever. But radioactive decay, look at this. This is 1 million kilojoules of energy per gram. That's over 1,000 times as much. In fact, it's over 10,000 times as much. That's a lot of energy. Okay, so when we compare them, radioactive decay gives us a huge amount of energy. So, kind of giving you a graphic for that, right? If I were to take 4 paper clips, if I could convert those to energy, that would give you enough energy to heat your home for 1 year. If I were to take it's about 15 tons of coal. Right? So you look at a train car full of coal, that's a bunch of coal. Think of it as the entire senior class. If I took the entire senior class of the school, stuck them in the middle of the gym, and made them all sit in a pile, one on top of the other, right? And then converted that to rocks, to coal, that's how much energy you use in a year to heat your home. Right? Whereas to heat and cool your home. And here I could use the amount of energy in 4 paper clips of uranium. Wow. Which one is better? Interesting question. All right. So we would like to be able to use nuclear energy for generating power. However, it's not always a good candidate for that because it's very hard to control. Its rate of output is not constant. You'll see that in the next slide. Right? Isotopes with short half-lives give off lots of energy, but only for a very short period of time. But if they have a long half-life, then they only give off a little energy. Now, granted, they give it off for a longer time, but they're only giving us a little energy. And as each half-life passes, less and less energy is released. So think of this kind of like a pile of wood, right? If I put a pile of wood on the fire, realize that the concept of nuclear energy is essentially it instantly starts burning and all of it is burning. And then pretty shortly, there's only half of it left, so I'm only generating half as much energy, and pretty soon there's only half of that left, so I'm generating less energy, etc., until I'm generating virtually no energy. All right, so that's essentially what's going on here. All right, so if I look at this graph, if I start with what's called a parent isotope, it's 100% of what I have, right? And I start using it, it's going to generate a lot of energy at first. So this is the amount of energy I'm generating here. All right, I'm generating lots and lots of energy, right? But then I get to this point, and I've gone through 1 half-life. And at this point, only half of my original stuff is still here. Right? So I've generated all this energy. Right? But then only half of the stuff is here. So now, all of a sudden, I look at this next time period, which is just as long, and I'm generating only this much energy. And then my next time period, I'm generating only this much energy, etc. So it's going down by half every single time. And I'm getting these things called daughter isotopes. All right, so I may be getting something that is completely useless to me, like lead, right, which is not going to decay anymore. Now, there are some things which decay and their children decay as well. And we'll talk about that. But this is the concept of your energy is dropping very quickly over time. And you're getting all of this waste material, which is this stuff. Right? So when do you stop using this? Do you stop it here? Or do you stop it after 2 half-lives or 3 half-lives? And then this stuff is still going to decay all the way out here for years, thousands of years. So what do you do with the stuff as it's still decaying out there? So one problem is that energy production is front-loaded. Look at this and you see that your energy production, the massive major part of your energy is up here. And then after that, you get very little. All right? And we did say that our children, our daughter isotopes, could conceivably decay also. Right? So again, we have the potential for radioactive isotopes there. How long can something be radioactive? Literally thousands of years, millions of years, billions of years. Right? So that is a potential problem. Right? Now, if you remember U-238, you should have done this on one of your worksheets. There were 14 steps in uranium-238. So it did not just go through one decay. It went through 14 decays until it hit something that was stable and would not continue to decay. Some of those decays happened very quickly, in less than a second. Some of them took thousands of years. Over time, scientists have created over 1,000 artificial radioactive isotopes. Many of them aren't useful for much. But there are some things, for example, technetium-99, which is used to detect brain tumors. Now, if you look at the technetium chart on its number 43 on the periodic table, I think, if you look at it in our classroom, you'll notice that it's outlined. And it's outlined because technetium does not exist in nature. However, we have created it. And technetium-99 is radioactive, and it's formed by bombarding molybdenum-98 with a neutron. Now, it also produces a beta particle, but the thing that we really want is this stuff. And why do we want technetium? Well, we use it in the medical field to trace tumors, right? And we'll talk about that again in a different podcast, but that's what we do. We create it. All right, we've got 4 examples where we're going to go through and we're going to bombard things with other particles, and we should be able to figure out what the nuclear equation is for that reaction. All right, let's try that again. We have calcium-40 producing potassium-40 and another particle. So let's go and write this equation. This is stuff we need to be able to do. So we have calcium-40, which is producing potassium-40 and something else. Well, let's see what we have. We have calcium. If we look on the periodic table, calcium is number 20 and potassium is number 19. So since we only have one other particle, we know that our mass isn't changing, so the top number has to be 0, and our bottom number has to be a 1, because 19 plus 1 is going to give us 20. Right? If we look at that, what in the world... try this again. I did not do that right. Let's try this again. Calcium-40 is hit with a neutron. Sorry. It's one of those days. It's hit with a neutron. Neutrons have no charge. They have a mass of 1. Right? So this makes something. I have a total of 41 on top and 20 on the bottom. So if I look at my mass is a total of 41. And on the bottom, my number of protons is a total of 20. So if I look at what it's producing potassium-40, which is there. Right, and potassium is number 19 on the periodic table. Calcium is number 20. Potassium is number 19. But I have to produce another particle. Well, I notice that my total has to be 20. I've only got 19 so far, so I need one more to make that happen. And my mass is only 40, and it has to be 41, so it has to have a mass of 1. So that means this is going to be hydrogen. or a hydrogen nucleus at least, a proton, right? So that is what I'm producing. That's my other particle. It's a proton. All right, let's try another one. We have beryllium, and it's bombarded with an alpha particle. So, beryllium, can you do this one? Go ahead and pause the video, see if you can give it a shot. All right, beryllium is number 4 on the periodic table, and we are told this isotope weighs 9, and we're hitting it with an alpha particle. An alpha particle, if you remember, has a mass of 4 and has 2 protons. Do you want to pause the video, see if you can figure it out? Okay, well, our total on the top is 9 plus 4, which is 13, and our total on the bottom is 6. And it tells us we're producing carbon 12. So there's carbon. Carbon is always number 6 on the periodic table. Well, the 6 is right, but the 12 isn't right, so I need to add an additional 1 up here. So if it's a 1 over a 0 means there are no protons and has a mass of 1, so that would be a neutron, if we think of what our particles are. All right? Let's try another one. Why don't you pause the video, see if you can figure this one out. Plutonium. Its mass is 239, and it's bombarded with a particle. Interesting. Don't know what it is. All right. So this is going to produce curium, and curium is Cm, and it weighs 242, and a neutron. And a neutron has no protons, has a mass of 1. All right. So our top number has to be a 243. And curium, if we look curium up on the periodic table, we find that that's 96. And let's look plutonium up on the periodic table while we're at it, and that's a 94. All right, so 96 plus 0 is 96. So our total of everything on the right is 243 over 96. So what has to happen here? Well, I'm going from 239 to 243. That's a difference of 4. And I'm going from 94 to 96. That's a difference of 2. 4 and a 2, that looks like a helium nucleus to me. In other words, that's an alpha particle. So 239 plus 4 gives me 243, and 94 plus 2 gives me 96. All right, let's try this one. This is the last one. A little bit more complicated. Give it a shot on your own, then I'll help. All right, uranium, 238. 238. And so that's a 92. Uranium is 92, and it's hit with some isotope of carbon. So let's see, that's going to be carbon. That means it's number 6 on the bottom. Right? And so that's a total of 98 on the bottom, and I don't know what the top is going to be yet. It produces californium 246, californium, and californium is Cf, and that's number 98, and it produces 4 neutrons. So I'm just going to write them out all separately as 10N plus 10N plus 10N plus 10N. All right, so that's 246 plus 1 plus 1 plus 1 plus 1. That's 250 up on top. All right, and my 98 is on the right. My 98's in the middle. 98 works just fine, but what I have to figure out is 238 from 250. That is 12. So we hit it with carbon 12, the very common isotope of carbon. So that's cool. All right, folks, that's it. You should be able to do nuclear bombardment reactions now. So go ahead and do them on your worksheet. Make sure you understand them and check your answers. And if you have questions, please see one of us in class. We'll be happy to help. Have a wonderful day.